Hello, Professor Yao. Let's start. Thank you for coming this Tsinghua-Yau, Tokyo workshop on Calabi-Yau. This research exchange program was proposed by Professor Yang, including IPMU and Jixiang. So let's start with Professor Yao's opening speech. Would you start, please?
Yeah, thank you very much indeed. I think it's a great idea to have a close collaboration between Tsinghua and Tokyo on such a important topics in geometry. And I'm grateful to Futaki and several other colleagues who worked hard on this conference. I was prepared very well to come physically. Several things happened, partly due to I've been traveling too much, and I like to physically take some rest. But also, I was involved in some important mission today. In fact, you can probably see that I dressed up because I went to the central government to discuss about funding for our center, including BIMSA. So I'm sorry I could not do it. Although I was very excited and feel good if I can come to admire the Fuji mountain, which I always like to see. And I have been in Tokyo many years ago. In fact, I think the first time I came to Tokyo was in 1977. So almost 50 years ago, we had a great conference between America and Japan on geometry, dependent geometry, where I learned a lot from the conference. In that trip, Jim Simons and I and Lawson, we were young at that time. So we were young participants in the conference, and I still remember it very well. And it was organized by Professor Chen, and Professor Kobayashi, and I think Yano and several other prominent Japanese mathematicians. So this kind of conference has been very useful and important for promotion of ideas in geometry and other subjects. And after those conferences, I also attend several conferences in Biwalik, Tenakuchi conference, and all that. And I've met many colleagues from Japan, and they are very good to communicate between us and Japanese mathematicians. Also, after that, I had some students from Japan. Bando was my former student, and he has been, of course, one of the very best geometers. And I'm really happy to see that he developed to be a first-class mathematician. And later, of course, I see many important colleagues from Japan, including Mabuchi and Futaki, and all this has contributed dearly and in the most important way to the subject of Kähler geometry, which I'm very happy to see. And of course, I also knew Professor Kobayashi very well, and Professor Kobayashi was the key person to help me to study in Berkeley, and I'm grateful to him for his help. But also, I knew Professor Ochiai very well about 53 years ago in Berkeley, and he has been a good friend. I'm happy to say that I saw him a few years ago. He was in good health, and I wish that all our friends in Japan continue to communicate with us and build a good relationship. And right now in BIMSA, also in Tsinghua, we have quite a few Japanese mathematicians working with us together, and I'm very happy to see them. In fact, we were talking with Professor Oguri and several other mathematicians. We hope that we communicate much more. I have been working with many Japanese postdocs, especially Professor Yamaguchi. We did a very good work about 20 years ago. I still remember the work. is related to BCOV in Calabi-Yau manifolds. All these, I think, are fascinating. The development of the Kähler geometry with string theory has been extremely fruitful to both physics and to mathematics. And to me, of course, the subject of Calabi-Yau manifold would not have been so fruitful without the input from string theory. The introduction of several important tools from string theory really has enriched the subject tremendously. Without the input of physicists, I think it will take 10 or 20 more years for Kähler geometry to develop up to the point that we are seeing now. So I'm very glad that this happens. And later, of course, several people in geometry analysis gave a lot of important works in Kähler geometry, this including the recent works of Simon Donaldson and many other great geometers. And I think the subject of Kähler geometry, including Calabi-Yau manifolds, are really flourishing and will contribute greatly to geometry. I believe that it will play an important role in algebraic geometry. And at the very beginning, I think this is the important trend. So I actually personally work on several things related to the people involved in the subject. And I think this is a great tendency that people are paying attention to geometric analysis. So it is a subject that includes algebra, geometry, and analysis, and in the most fruitful manner. And I think powerful manner, both to physics, to algebraic geometry, to differential geometry, and to analysis. These are all four subjects that are playing an important role. But actually, I believe in the future, number theory and representation theory will all come into this theory, which I think is great that it could happen like that. Okay, thank you very much for the organizers for this conference, and I'm grateful to all of you. Thank you. So should I start my lecture now?
Okay, let's start. The first speaker is Professor Yao, like LYZ equation and the CJY condition. Let's start.
Okay, thank you very much. So today I'm going to talk about LYZ equation and the CJY conjecture. The LYZ equation comes in the following way. As we know, in the most fundamental level, meter symmetry come into string theory, and in particular, come into Kähler geometry. It gave rise to a framework for treating different Calabi-Yau manifolds. These two Calabi-Yau manifolds may be topologically distinct, and it is rather shocking to me when I learned they are related. This happens in 1988 and 89 when Brian Green, who was my postdoc, came into my office and explaining some examples, majorly on the quintet. And this was spectacular because after Green and Pezer's work, there was a very major contribution due to Kähler and his group, did a very profound calculation on the quintet. This has been a major input to Kähler geometry by the string theories. So meter symmetry is fantastic. It defines a duality between the underlying structures on each manifold, and the development of this elegant theory has led to progress in a major manner. So the particular aspect of the meter symmetry we are interested in is the relation between the derived category of coherent sheaves on one manifold and Fukuyama's category of Lagrangian submanifold with local systems on the other. And this was proposed by Machine Conservage and Fukuyama, and I think this has been a very important guideline. for the development in Miller symmetry. But in 1995, in a differential geometric manner, independently, Conjecture and, well, not Conjecture, Shing-Tung Yau and me developed so-called SYZ conjecture, which put the Miller symmetry in a more geometric way in terms of T duality on the fiber length by toroid, Lagrangian toroid. And this has been very fruitful proposal, although the proposal has not been proved, but in the last 25 or 28 years, many important consequences has been derived, and many of them are still good. And it seems that everyone goes in the right manner. So it's difficult to resist to look into that in more detail. And this was approached using algebraic geometry by Siebert, for example, and Mark Gross, and they have done a very fruitful and thorough understanding from algebraic geometry. And also, my former student, Conjecture, and leading a large group of his own students, has been also exploring the SYZ development in a very fruitful and contribute a great deal of important films. But in the simple case, Conjecture and Alex Sasso and I, almost immediately after the proposal of SYZ, we gave an explicit formulation of an equation on the line bundle that corresponded to the special Lagrangian equation on the Miller manifold. So specifically, let X and X hat to be due toroid vibration over a base and B on the base B. So X Calabi-Yau manifold, X hat is another Calabi-Yau manifold. Both of them has a map into B, and there's a fiber. The fiber is given by Lagrangian toroid. And in this case, we want to say that a connection on one of the homomorphic line bundle over X is actually due to a Lagrangian section of the toroid vibration, X tilde. So the fiber of X and X hat on the generic points are due toroid. And this has been explored very carefully by Jixiang after our work. I think if very nice guideline was supposed to be known and to be seen. So Conjecture and Sasso and I look at this X and X hat and try to make this setting explicit. So how to give Lagrangian section to the connection. And this was worked out. So if L is a special Lagrangian section, so it is a calibrate Lagrangian section, then we, according to SYZ, we use the Fourier-Mackay transform LYC so that A must satisfy the equation written in equation 1. So omega is a Kähler form, and F is the curvature of the connection. And we write down imaginary omega minus F to the power n is equal to constant times the real part of omega minus F to the power n. This is an equation that we can derive from the special Lagrangian section. Special Lagrangian has is a minimal submanifold. Is locally can be written as some graph of the differential of a function, and the equation can be written down. It was written down by Harvey and Lawson, and we imitate that equation and try to do the Fourier-Mackay transform. The end result is this beautiful equation sitting in here. Well, I call this LYC because people call it deformed Hermitian Yang-Mills. It's very clumsy to call it that way, I feel. And also, in any case, we were the first one who wrote down this equation. It is derived from the concept of supersymmetry by 4 physicists, Marano, Minasin, Catmull, and Schomburg. But they look at it in a different manner. Here, we look at it in a much more geometric manner, which is very important for the development here that we are talking. So let's be more clear. So let us write X comma omega to be a compact Kähler manifold of complex dimension n, and chi is a closed real 1-1 form on X. Well, at the beginning, chi was considered to be the first Chern form of some line bundle. But in reality, look at the equation, we don't need it to be an integral class. First Chern form is always an integral class, but you can just take any closed real 1-1 form. That's all we need. Then the above equation can be written as equation 2. So you just replace the curvature to be this. And this is chi u is rewritten of the original chi, the first Chern form or the 1-1 form plus a dd bar of some function. So this is any form, 1-1 form sitting in the same class. So the equation 2 is therefore the equation we are interested in. Once you have equation 2, then you know how to write down the cotangent theta hat, because there's a constant. You can integrate the left-hand side and the right-hand side of equation 2. You found out that theta hat is actually the argument of the complex number obtained by integrate chi plus I omega to the power n. So this is a kind of phase that appears in string theory, actually. Now, suppose I take lambda, lambda 1 up to lambda n to be the eigenvalues of chi u with respect to omega. So use omega, the Kähler form, as a background. We can write the Hermitian form chi u, and you have eigenvalues. And lambda I are the eigenvalues, and we write lambda I to be cotangent theta I. So theta I is arc cotangent of lambda I. And then we can compute in the chi u plus I omega to the power n. And the simple calculation, you end up with this equation I wrote down here at the bottom. So that's the equation. So we can look at the real part and the imaginary part of this equation. The real part is cosine of summation theta I divided by product of psi I, psi theta I. And then you write down, you translate the equation, and it becomes the following equation. So the LYC equation, as was discovered by Leung, Mills, and Sasso, is cosine of the summation theta I equal the constant, the phase cotangent theta hat psi summation theta I. So it becomes a rather simple equation. The equation that we declare is cotangent of summation theta I equal to cotangent theta I bar, where summation theta I is summation arc cotangent lambda I, and arc cotangent lambda I, the lambda I is coming from the eigenvalue of the chi u with respect to omega. So the simple equation looks, of course, simple, but it's all reasonably complicated. It's equation 3. Theta omega chi u is equal to theta naught, where theta omega chi u is defined to be summation arc cotangent lambda I. So this is the equation that appear in the LYC paper, which is the mirror of the Lagrangian special Lagrangian cycle. Now, theta naught actually can go from a wide range because it's a lifting, and it can. We shall assume it is in the range between 0 to pi. When it's beyond that, the problem becomes quite a bit more complicated. So most of the argument, the advance that we make, are assuming theta naught is in the range between 0 to pi. Well, so the equation can be looked at as a complex version of the special Lagrangian cycle for graphs. And theta naught is the analog of Lagrangian angle, and lambda I is the analog of the eigenvalue of the Hessian generating function of the graph, if the Lagrangian cycle is locally defined by graph. This duality is actually very important. But on the other hand, something mysterious is when the graph is not quite defined globally, but only a multi-graph, the multi-value function defined by, this becomes far more complicated. So when the when the section of the Lagrangian is a single value, is much easier. Anyway, this equation has been extensively studied by many mathematicians, but it has never been really solved, except very simple case until in 2014, when Adam Jacob came to Harvard as a Benjamin Pierce instructor. Then we worked together, and I proposed to study this LYC equation to try to solve it. So the first paper in the analysis part of this equation was started by Jacob and myself, appeared in Math and Ireland in 2017. This special Lagrangian type equation for holomorphic line bundle. When n equal 2, that means in the case of complex surface, we prove that the solution exists if and only if there exists a function u such that chi u hat is chi u bar is bigger, strictly bigger than cotangent theta naught omega. So in other words, if I write that alpha to be the difference between chi u bar minus cotangent theta naught omega, then we are requiring alpha to be a Kähler metric. But in that case, in n equal 2, we can derive the LYC equation into the complex motion pair equation of this type. Alpha plus I dd bar u to the power square is equal to 1 over psi square theta naught times omega square. This was solved by the Calabi conjecture. So we know that it exists in the case n equal 2. And for n bigger than equal 3, things are more complicated. Then Adam Jacob came first, as I mentioned. Then in a couple of years, Tristan Collins come to Harvard also as an assistant professor, Benjamin assistant professor. We work together. We solve the LYC equation for theta naught belongs to the interval 0 to pi by assuming the following two conditions. Number one, there exists a sub-solution U hat, which means that chi u bar satisfies this inequality 4. This inequality is kind of like a sub-solution. And we, at that point, make an extra condition, which we know should be get rid of in any case, namely theta omega chi u is less than pi. This paper appeared in 2020, although it was done quite a bit earlier, in Cambridge Journal of Mathematics. So this is the first major step that we make for this LYC equation for arbitrary dimension. So in effect, the precise equation freedom that we prove is the following thing. You let x comma omega be a compact Kähler manifold dimension n, and chi is a closed 1-1 form with theta naught between 0 to pi. Suppose there exists a sub-solution of the LYC in the sense of 4, which I mentioned here, number 4 here. This is a sub-solution. And then we also assume it's satisfies this extra condition, number 5. Then we prove there exists a unique smooth solution of the LYC equation. So this is what we proved about 4 years ago, 4 or 5 years ago. And well, the definition of sub-solution, 4 is actually a sub-solution. The definition of sub-solution of fully nonlinear equation was introduced by Bao Guan. I'm not sure he is the first one to do it, but anyway, we learned it from his paper. And then soon afterwards, so Gabo, who was in Harvard as a postdoc also, in 2018, after saw our thing, he started to find an equivalent version and found that the work that we did for the LYC equation is equivalent to inequality 4. And there are several papers relate to this, and there's some generalization of this to non-Kähler manifold to compare almost Hermitian manifold, and also in the case of omega, Kähler class, Kähler form satisfy d bar omega equals 0 and d bar omega squared equals 0. So these are very special class of Hermitian manifold, although it does generalize Kähler matrix. So in 2021, there was this paper by 3 authors where they do it for almost Hermitian manifold. And then later, the important paper was due to C.M. Lin, appear in 2012 in the archive. Well, the condition 5 is found to be basically superfluous. When n equals 3, Pingarlin can solve the LYC equation without condition 5 by translating the LYC equation into a mixed motion pair type equation. When n equals 3 and 4, CM Lee can solve the LYC equation without condition 5. So that was a good work. And the most recently, CM Lee solved the LYC equation without anything, without condition 5. So it says that if there exists, given a Kähler manifold with chi closed real 1-1 form with theta naught between 0 and pi, there exists a sub-solution of LYC in the sense of 4. Then there exists a unique smooth solution of the LYC equation. So basically, he get rid of the condition 5 that we make the assumption in the paper of Collins and Jacob and myself. So this is a very nice thing to do. So now let us try to understand more about the conjecture that we make, Collins, Jacob, and myself. So denote capital omega to be the following quantity. Is take the difference between two guys, except the power p is not necessarily the dimension of the manifold. P is less than n in general, and we look at this difference. In the case p equal n, we are trying to prove the equality. So we define those 1-1 form to be p omega, which means that integral of this capital omega to be on any subvariety of p dimension over y is strictly positive. This is is an open set of 1-1 form sitting in the manifold. And then we look up another set of solutions, and open set S omega is the LYC equation has a smooth solution. So we conjecture after reading in all those related works, we conclude in the CJY paper that for any compact Kähler manifold, we believe that P omega is equal to S omega. So this was conjecture that we made about 5 years ago, although in published form is probably a year later. But anyway, so I consider this a very nice conjecture because what it means is that if we can solve the LYC equation, we get many interesting consequences, namely some trend number inequalities of this sort. And this was a very good conjecture, I think. It aroused many interest immediately. Gao Chen made a progress on this conjecture a few years ago. He wanted to study a smooth family, chi T, of real closed one form, which he called a test family. I guess he tried to compare with the K conditions, stability conditions. So the family satisfies the following property that when T equals 0, it starts from chi. Chi T is a family of real closed one form. The T equals 0 is original. And that chi S minus chi T is positive, definite. Then he wants to say there exists large enough number, capital T, such that for all T bigger than capital T, chi T minus cotangent theta naught over n of omega is positive, definite. So So Chen called this a test family. It appeared in his paper in 2021, a couple of years ago. He proved the following statement. Suppose we have a compact Kähler manifold dimension n and chi a closed real one-one form on X with theta naught between 0 and pi. Then he proved the following equivalent conditions, a very nice work. First of all, there exists a smooth solution to LYC equation. And then suppose for any smooth test family, there exists a constant epsilon, positive constant, such that for any t and p dimensional variety, this integral is bigger than this condition. So instead of just bigger than 0, he wants to say that it's slightly bigger in a uniform manner, namely bigger than or equal to constant times the integral omega p, the volume of y. And then there's another statement, is that there exists a test family, chi t and a constant epsilon, such that this also holds. So, so you want to say that these are all equivalent. That was his work. And this is a kind of idea learned from several people, starting from dHYM and Palm, and also Jixiang. Motivated by this work of Chen and Zhang, Zhu, Li, and Takayasu established the following nice theorem. It says that LYC equation on a compact Kähler manifold with complex dimension n is solvable when theta naught is between 0 to pi, if and only if there exists a Kähler metric such that this inequality holds. And so this is improvement of what the previous work is. And then they confirmed the CJY conjecture that we make for projective manifold. So this is a beautiful result and finally achieved after about 4 years of our conjecture. And this is a nice, beautiful argument also. Well, so Junxin Chen proved that S omega, as I described earlier, is both open and closed subset of P omega as the main theorem on the Kähler cone proved by dHYM and Palm. But then he disproved our conjecture, CJY conjecture, in the Kähler but non-projective case. The kind of example he gave is a blow-up of C3, a toroid, at a point where the toroid, three-dimensional toroid, is a three-dimension but with no positive proper analytic subvariety. So this is very interesting. So our conjecture is true for the projective case and not true for general Kähler manifold. So this gives you a lot of room to think about actually. Well, in the other directions, in the meanwhile, about a few years ago, 3 or 4 years ago again, Collins and I developed the Miller of the infinite dimensional GIT picture of the LYC equation, which we like to understand LYC in terms of this GIT picture. So we describe an infinite dimensional symplectic manifold emitting action by a group of symplectomorphism together with a space in the smooth functions H. And there's a Riemannian metric, and we found a Riemannian structure on this subspace, which can be thought as an analog of G mod K in the finite dimensional GIT. So we all know that the famous geometric invariant theory developed an interesting way to understand the moduli space. We try to do it too. We compute the geodesy equation since we have a metric, Riemannian metric on this infinite dimensional space H. We introduce a notion of epsilon geodesic, which solves an approximately similar version of the geodesy equation for this metric. This paper appeared recently, although it was on the archive for quite a long time. We introduce the compressified Calabi-Yau functional and extract from this functional analog of the C and the I functional made by other people. The I functional is a Kempf-Nash functional for the GIT problem. It has critical one. It has a critical point as solution of the LYC equation and is convex along smooth geodesics. Most of this functional actually appears in my proof of the Calabi conjecture. So a fundamental issue in this analog with finite dimensional GIT is actually the following question: whether smooth geodesic exists or not. It may not exist, but in order for the analytic contribution to work well, we need to prove that in the hypercritical phase case, the weak geodesic connecting points in this many infinite dimensional manifold, it has some regularity, more than C1, namely C1 alpha. This is important for many discussions later. This alpha Holder continuity argument. Only with this regularity, we can show that the functional are well defined and prove that they are convex or concave along those generalized geodesics. So we need the regularity of the geodesics so that we can play around with these functionals. So now with this result in hand, we can put the setting of infinite dimensional GIT problem with geodesics playing the role of one parameter subgroups that appears in Munford and other people's work. And using algebraic geometry, we construct model infinite rays similar to the one parameter subgroups in the space H. And we can evaluate the limit slope of the Calabi-Yau functional along these model curves in terms of algebraic data. So this rather nice, using the existence of regular geodesic, these model curves give rise to algebraic geometric abstraction to the existence of solutions to LYC equation. So an example is that we prove that in a hypercritical phase case, when theta naught is between 0 to pi/2, and we take a sequence of ideal sheaves of the structure sheaf. So I1 belongs to I2, etc. And we can define a sheaf over OX. OXX is the original Calabi-Yau manifold and tensor of CT. And then we look at a log resolution of this ideals, this sheaf on X cross delta, the disk. And we look at the inverse of this sheaf. It becomes a OX of minus E for some simple normal crossing divisor. Then we prove that if chi emits a solution of the LYC equation, then this inequality holds. So this is an interesting stability condition that arises in this consideration. And we still need to develop more about this. And we were hoping to try to identify all these conditions with the Bridgeland stability conditions. And it's being developed in low dimension, and we have not really completely understood the whole thing yet. Well, there's a parabolic version of this work. It's already started by Jacob and myself, and Tristan, Colin, and Jacob and myself, where we start the line bundle mean curvature flow, where we just develop UT, the heat equation analog to equal theta naught minus theta omega, starting from a subsolution of the LYC. And we can prove existence and convergence for the long term solution in the case theta naught between 0 and 2 pi. And so this was good and it was helpful. And then later, Han and Jin consider the stability result of this flow. And Takahashi proposed a little bit somewhat different flow, put a tangent there. So he called tangent Lagrangian phase flow, and he did a good work also on this one in terms of convergence of the long-term solution. And for the case theta naught between 0 to pi/2, and theta omega chi u bar minus theta naught belongs to minus pi over 2 to pi over 2. So this appeared a few years ago. Well, motivated by the concavity of cotangent theta omega chi u by Chen, Fu, Chen, and myself, consider a new flow. Namely, we write down this equation 8, where we replace the flow by cotangent theta omega times chi u minus cotangent theta naught. And with the theta less than pi, this we studied the deformation, and this we can prove existence film for the long-term solution of the flow. So we prove that if X is a compact Kähler manifold and have a chi to be a closed one-one form, and if U naught, the initial data, satisfy this inequality, then the flow exists and has a unique smooth long-term solutions. So this was nice, and in fact, suppose there exists subsolution of the LYZ equation in the sense of 4, which also satisfies 5, then there exists long-term solution of omega with U naught equal to U and converge to a smooth solution to the LYZ equation. So we can prove in this flow argument, we recapture the original theorem that Collins, Jacob, and myself, and the parabolic version seems to be natural and proof is simpler. The advantage of this new flow that we developed is that the imaginary part of the Calabi-Yau functional is constant along the flow, which is an important part to prove the CCO estimate for this way. Well, the flow is being developed. Now, let's recall the definition of complexified Calabi-Yau functional that Tristan, Collins, and myself did. So given a function V, which is a smooth function, C2 function, we define this functional appear here. This functional actually appears in my proof, the Calabi conjecture, interpreted in the right way. And then we call it CYV, and then we differentiate this CYV if V is deformed in the following way. You take a Vs to be on X cross the deformation parameter, CL to T, and initial data is equal to V. Then we differentiate the Calabi-Yau functional with respect to S. We come up with the right-hand side. This right-hand side is very nice. This is exactly what we like to see. So that's why we developed this Calabi-Yau functional in this way. And we also have this following Hana type inequality along the flow in the CCO estimate. Namely, if U is a solution of the flow A, then there's a constant here independent of T in the imaginary part, as I said. This is important for the CCO estimate. And well, in here, we also prove that limit UT equals 0 is on a complementary of some EIs under some semi-subsolution condition. So we prove that importantly is that there exists a uniform constant so that the real part of the Calabi-Yau functional is bound uniformly by the L infinity norm of U as long as the theta is less than pi. So we also prove that the equation under existence of semi-subsolutions, we can prove the equation existence. And so this has been useful to solve the equation using the flow. And a smooth solution, we call it semi-subsolution if we satisfy this equation 11. In this case, there exists a semi-subsolution, and if there exists a U naught satisfy this initial condition. So anyway, this is the film that I did recently last year with Fu and Chen. So let X be a compact Kähler manifold with chi a closed one-run form. Assuming theta naught satisfies this inequality, then there exists a finite number of curves of negative self-intersection number on X, so that the solution of the flow converges to the bound function in the complement of this E. And it has the following property that the difference is a Kähler current, which is smooth outside EI, and U infinity satisfies the LYC equation. So chi UXT converges to chi U infinity, and U infinity satisfies the equation 12 on X in the sense of currents. So this flow does give you some interesting properties in terms of EI and all that. So I think this is a very nice thing, except this works only in 2 dimensions so far. And well, a similar result of J4 was obtained by Frank, Lai, Song, and Wenko, and also Takahashi proved the same convergence result set for the equation 6. Well, if we the LYC equation may be degenerate. So these are very interesting to study what to do when the equation becomes degenerate. And these are related to semi-stable cases of the Hermitian Yang-Mills equation. And it's interesting to compare with what Simon Donaldson do 40 years ago in terms of existence of Hermitian Yang-Mills using flows. Now, so this last 3 pages was description of the work with Fu and Chen. Well, now let's outline some of the speculations that we like to make. Sometimes we can solve the LYC equation by different means. In this case, that we will give rather important, interesting consequence for the algebraic manifolds. So 5 years ago, when Tristan Collins, when I studied this thing, we observed that if the projective manifold is covered by a homogeneous manifold, so a manifold with automorphism very large, then we can solve the LYC equation by using homogeneity, by reducing it to some pointwise calculation. Good examples are abelian varieties or Shimura varieties. So abelian varieties are covered by CN, and Shimura varieties are covered by Hermitian symmetric domain. All these are symmetric spaces, and they have a large group of automorphisms. So we can reduce the LYC equation to pointwise calculation because of that. And once it's done, the invariant Kähler form and the invariant monoid form together give rise to a solution to the LYC equation. And as a result, it gives a range of Chern number inequalities over algebraic subvarieties. And this is not trivial, seems to me, for that such a Chern number inequality holds for algebraic subvarieties on this locally homogeneous manifold, even for abelian variety. So it would be nice also to find out what happens when these inequalities become equalities. This is similar to Kähler symmetric, where we found some Chern number inequality. When the inequality becomes equality, some interesting rigidity result appears, and they become rather interesting. Now, so if a closed PV form, we conclude that if a closed PV form can be represented by an effective algebraic subvariety, there's some inequality must hold, come from these LYC equations. And I believe this inequality would give non-trivial information about the Hodge conjecture, because this shows that if a closed PV form is representable by effective algebraic subvariety, the further constraint has to hold, namely those Chern number inequality on the subvariety. So I believe this needs to be explored more. Okay, I think I will stop here for this talk.
Thank you very much. Are there any questions? you talked about the stability conditions. I think I saw in our chance work, number 2 looks like uniform stability. And also you explained about some blow up the ideas. Also, it seems the quality concerning theta looks like some stability condition. Are there some relationship or not?
Right. I think it's very interesting to explore more under what condition they will become equality, and also what condition we impose on those closed PV form. These are statements that was not seen before by using Kähler answer metric only. Kähler answer metric has been useful to dealing with second train class and first train class. But here we are dealing with high train classes. And this set of some nice inequality, I think, is an interesting thing, which has not appeared in algebraic geometry.
Thank you. Are there any other questions?
Is there any example in which the obstruction is described by return stability?
By what?
Is there any example in which the obstruction is described by return stability?
Well, we're trying to compute the obstruction for interesting case in relation to Hodge conjecture. And sometimes we thought we can disprove the Hodge conjecture, but we overlooked something, so we could not say for sure. But in any case, you give a hint and or lead to see whether there's further constraint on a closed PV form to be representable by effective algebraic subvariety. We are still trying to compute it. The computation is not trivial. So we are still trying to see what happens.
Are there any questions? Not, let's send the speaker.
Okay, thank you. Thank you for the talk.